Hello everybody, welcome to today's webinar. My name's Matt. I work in the customer support department here at SMT, and we're going to look at system deflection analysis in MASTA today. Okay, so I've done a brief agenda of what we're going to look at. So we'll do a quick introduction into system deflection. We'll have a look at how the system deflection model works and how some of the components in system deflection also work, and some of the results and some of the settings that we can do with those. So the first thing to look at is what is system deflection mode. We have it's an FE-based analysis that we have to look at the full system of your transmission under the boundary conditions that you've specified. It's also used in the microgeometry mode and the LTCA calculations, which then get fed into the MVH calculations, which would be very useful. And also it's used in the parametric study tool, so that you can vary other parameters to see how they affect your results. So what we'll do now is we'll have a look at MASTA, and we'll get into system deflection mode, and we'll have a brief look at how this works. So what we have here is our example transfer case model. You can see here that we have a basic transfer case model, and we have all our components, shaft profiles, everything defined here in MASTA. Now, what MASTA does then is it has a look for anything interesting that you have on this model. It calculates the stiffness, uses different calculations for different components. So for the gears and the bearings, we have bespoke non-linear models. For the shafts, we use the Timoshenko beam model, and also if you have any FE components in there, these are also added into the model. So this gets simplified down to this node model here that you can see. So this is a representation of it, and then the boundary conditions that you have will then be applied to this model, and you can see that the system deflects in this way. So in system deflection mode, we have to start with, we have a 2D view. So once we've run this, we have a few options to have a look at the 2D view in here. So the first option is we can have a look at how the power is flowing through the system. So you can see here that we have a path of power running through the system. We also have a distinguishing between high power and low power. So the darker the line, the lower the power. We have a few more options up here in the drop-down menu. So we can have a look at the axial loads in the system deflection model. So there's a lot here. So we can also have a look at the axial loads that are provided just by the gears. So you can see if there's anything that you're seeing in your results and you want to have a look how they are actually happening. It's a nice visual aid for you to get some ideas as to what might be happening in your system. We can also have a look at the bearing truncation. So if we zoom in on the bearings here, we can have a look that once we've run this load case, we have a red line here around the bearing showing where the truncation is occurring, or where it is likely to occur, and where it's closest to truncation happening. And last in this tab, we also have the bar model. We have a couple of other options as well, like the shaft deflections, but we won't focus on that right now. We can have a look in the bar model at these shaded sections as to how MASTA is building the node model up. So we can see here that the shaft is being extended out, and this is how the stiffness is being calculated for your model. So after that, we also have a 3D view. So this is similar to the 2D view that we were just looking at. There's some similar information that we have. Again, it's a nice visualization to see if there's something that you're not expecting in your model. You can see the reasons behind this. So if I turn the components back on here, we have a look around. We can have a look at how each component is deflecting. So this is quite exaggerated, but it gives you an idea of what's going on here. We can also have a look at the force arrows and have a look at where the forces are occurring. If we move down to, say, this just this gear set here, we can have a look at the forces that are going on in the gear set and the deflections. We can also have a look at the contours that are happening on there. So we can have a look at the stresses and the displacements. So we can have a look at the magnitude of the displacement on the model. So the first component that I want to take a look at here is the gears in MASTA. So what MASTA will do is it will take a system level calculation and apply it to the ISO calculation that many of you will be using. It will also do the same for the AGMA calculation if that's what you choose to use as well. In system deflection mode, this will take the misalignment for the gears, and as we saw in the model here, we can calculate the misalignment on the gears. We'll turn the component off, and this, you can see here the mesh nodes. So when we turn the deflections right down, this is under no load, and then as the load increases, we can see the deflections on these nodes, which will then be used to calculate the misalignment, which can be fed into the ISO calculation. And then we can take a look at this in the report here. This is something that you'll see as you go through the modes in MASTA, that you'll see the source of certain values for your standards, and it will give you the source of these. So in this case, the misalignment is taken from system deflection, and other factors will be taken from ISO 6336. I'd like to take a look at the effect of the mesh nodes in MASTA as well. So what we have is in this model, we have an option on the left-hand side on the root assembly to change the number of mesh nodes in the node model. And for this one, depending on how stiff the rim of your gear will be, we can either increase the complexity of it by increasing the number of mesh nodes, or we can reduce it if you've got a very stiff gear. And we can do that down in the properties grid. There's lots of other things that I can show you in the properties grid in a little while as well. But you can see that in this case, if I go back to the cylindrical gear train, and we have a look at the duty cycle report, that we do have a little bit of difference in the misalignment here, which you may want to capture in your model if you're running quite a later analysis in your project. Then this will be quite significant, and you'll probably want to make sure that you capture this correctly. Something for sorry, before I move on, this one here is for the single mesh node, where we get a little bit more misalignment than if we have just the 5 mesh nodes by default. We can have a look at this in the 3D view as well. And then this one here just uses the single mesh node. So you can see that this one here has a single deflection, and then this load case here, we get we can zoom in a little bit more to see this better, where it's a less regular deformation. You can also choose the microgeometry. So if we go into the load case properties, we can go to the cylindrical gear meshes, and we can choose the microgeometry model that we use in the system deflection mode. Now, when we do this, we can choose the estimated from macrogeometry option, which is the one that we would recommend for when you're building your initial models. So this adds a bit of lead relief and crowning, just to reduce the edge loading. We have the option for none if you would choose, if that's something that you would prefer, but this is a very conservative model, and that's not the one that we would recommend. Again, if you're quite a late part of your project, you can also choose the microgeometry that you have specified for the model, and you can use this in the system deflection analysis as well. And when you have this selected, it will be used in all of the system deflection calculations in all of the modes. So that's quite important there. We can see as well that we can override other properties. Now, what this will do is it will, when we looked at the reports in here, we can see that the system deflection was the source of the misalignment. So we can override this, and we can say, I want to see what my load case is like if I have a misalignment of a different value. So we can override this here. We can also override other ISO 6336 influence factors. And we also have the option to change the planetary load sharing, but I'll have a look at the microgeometry first, just to show you the effect of this. So if I look at this in the 3D view in system deflection mode again, if we put the force arrows on, we can see that there's a nice load distribution on these gears. And then if I have a look at the load case here with no microgeometry, we can see that the force is much less like what we're looking for. Now, I know that that's not how we're going to have the transmission designed, but this is going to be far more conservative, and you're not going to get anywhere near the results that you would be expecting. We can also have a look at the planetary load sharing. So in this load cases mode again, we have planetary inputs. Now, a lot of the planetary inputs are to do with advanced system deflection, so we won't have a look at that. But we have the option for the analysis results. Now, this will just use the planetary load sharing method that you've selected in the design mode. We have distributed to give the worst damage. We have single planet taking the peak load and others taking the equal load. So these two will give slightly different results depending on the load sharing factor that you've specified in design mode here. So we have so that can be done here in design mode under the planet carrier component. And you have the choice down here of planetary load sharing method, and you can use the AGMA or user defined or equal, or the GL option down here, depending on what application it is that you're using. Okay. So we can move on to the shaft components now. If you have any questions about the gear calculations in MASTA, then please let us know, and I can try and go through that at the end, or if we don't have time at the end, then I'll get that back to you. So after we can move on to shafts here. We can have a look at the reports on the shaft. So we can have a look at the deflections on the shaft, and as I said before, this gets turned into a single beam, the Timoshenko beam model, and into a series of nodes here. We can have a look at the deflection at each point here and the stresses that are put upon the shaft at each point by going into the shaft report. And if we scroll down to the bottom, we have some diagrams here, but I can show you the next tab as well, where you'll see these a bit clearer. We have the connection forces to the other components, and we have the node forces as well. So this is each node on the shaft, and you can see what forces are applied to these and the deflections. But it may be easier to see this in the shaft results tab, where we have the X, Y, and Z deflections plotted here, and in the bottom left corner we can choose our different results that we want to have a look at. So we can have a look at the fatigue damage. We can have a look at the linear magnitude of the displacements on it. Now that pretty much covers the shaft. There's many ways that you can view your results there, and now we can move on to the bearings, where there's a bit more involved with this. So for the bearings, it works in a very similar way to the gears, where we take the standards and we can feed in the results from the MASTA system model, and we can improve on the standard results that you may have. So down here we have the misalignments and the loads upon the bearings. So we have these for ISO 281, ISO 16281, ISO 76, and if we scroll down a bit further, we also have the DIN 732 rating. Okay, and then we have some other charts as well where we can see the stresses, but we also have a tab up here where we can see these charts, a bit like the shaft results that we had. We can see them in the full screen, and we can choose which results we want to see on these charts, and we can also see the stiffness for the bearings. So this is the stiffness that's calculated using our bespoke nonlinear model, and then these are the numbers that will be processed in the system deflection model to produce the loads for your calculations. And then as promised, here are the charts that you can see. So we have the stresses upon each individual element in the bearing, and along the length of the roller as well. So with the bearings, there's a few settings that you'll want to look at. So in the load cases, we have some bearing inputs here. So we have the option to change the axial internal clearance or the radial internal clearance depending on the bearing type, and we can override them on a load case basis. Now, the reason for being able to do this is when you want to have a look at the optimal clearances, you can have a look at this in the parametric study tool, and being able to change these on a load case basis means that you only have to run one calculation without changing the design to view the results. We also have the option of putting mounting errors in, and also temperatures. You can do the temperatures in the load case settings as well for all of the bearings, or you can do them all each individually in the load cases bearing inputs tab. Okay. Something that is also important with modeling the bearing results in MASTA in design mode is the mounting options down here. So in more recent versions of MASTA, we've now been able to specify an axial and radial mounting for bearings. So this will have some effect on the results as well. So you can see the axial mounting can be constrained to either left, right, or both or none. And the radial mounting can be defined as interference, sliding, or clearance. And now this would depend on how your bearing was fitted in your transmission. We have the option to add preload here as well, which can be overridden on a load case basis. When you specify the when you're looking at the bearings in MASTA, you also have the setting here to include the fitting effects and thermal expansion effects, which will then override the it will override the what you've put in that box there, as the thermal expansion will take priority over that, and the fitting effect will. We have some load cases down here for thermal effects that we can have a look at. Now these are, let's have a look where we defined these. So we can define these thermal expansion effects here and the fitting effect here. I've set up a load case where we're going to have a look at the difference between the two, because it's quite important to make sure that this is quite right. So into the reports here. We can have a look at the bearing displacements and loads here, and we can have a look at the effect with thermal effects turned on. So we have the radial load here has increased with the effect of thermal expansion put on that. If you are looking at thermal expansion, it would be possibly quite a wise move to also include the thermal expansion of your housing that the transmission will have. So with the standard MASTA model, it can only expand in the way that it would know. So if we take a look at this 2D view here and go back to the transfer case root assembly, we can see here that this is where the housing is applied. So this one doesn't have any housing. So in the system deflection model, it's grounded here. So you have all these grounding points, but you also you don't have the geometry of the housing, so they can only expand out from these points. Whereas if we take into account having the housing on, we know which way the housing is going to expand and which way the forces are going to be applied as a result of this. So if we have a look at this duty cycle or design state here, we can view the different bearing results depending on which setting has been applied. So we can see here that the life varies quite significantly depending on whether you have thermal expansion on and with the housing, or whether you don't have any of this at all. Okay. I will also open a fresh example model here to show you the use of clearance bearings and their importance in system deflection mode. So we have this model here. So this may be available to you depending on licensing, the car transaxle gearbox model. Now, in the MASTA system deflection model, it's important that everything is defined correctly, as I've said before. But MASTA cannot detect the interaction of two shafts which are moving together. So if we have a look in the 2D view here, we can see that we have two shafts here. Now, with any help from MASTA, it won't know what it's expecting to happen here, and this will be able to deflect between the or through each other essentially. So we have to define those clearance using clearance bearings. Now, this one here is a radial clearance bearing, and we also have this one, and we also have an axial clearance bearing here. Now, what these will do is these will tell MASTA that there is a clearance, which can be defined down here. So we have the envelope, and we also, so this is the size of the clearance bearing, and we also have the stiffness, and we will have a clearance in here as well. So we have an internal clearance of 50 microns, and once this 50 microns is taken up, we will then have the very high contact stiffness being used from there. So we also have some settings to move on to. We have the, I will open the other model that I've prepared for this. We also have the effective efficiency that we can include in MASTA. Now, efficiency works down the system. So if a component gives a loss, then this loss will be transferred through to the next stage of the system, and the torque will be reduced through the system accordingly. So we can, if we press this button, we can see that it'll take into account bearing and seal losses. Fairly new is the clearance bearing loss as well. So we can look at the efficiency of our clearance bearings, and I can show you how this also has an effect. So if I go onto the efficiency duty cycle down here, you can see in this duty cycle I have one with efficiency and one without efficiency turned on. Okay, and you can see that in the load case with efficiency, we also have a difference in the loading. So this is in the bearing in the main shaft. So this is this bearing here. We can see the effects in this bearing too. And you can see that in the load case with efficiency that there's a bit of extra load, and you can also see that we also have the ability in MASTA to bring in FE components. So the FE components will change the stiffness of the system again. So if we look in system deflection mode here, so you can see this model here has a housing, and I have a load case here with no housing. We can look at the reports on we'll have a look at the gear set here and have a look at the effect on the misalignment. So we can see that we have this is the amount of misalignment that we have in this model, and we also have a load case down here which has the housing included. Now you can override this on a load case basis in the load cases mode, and if I click on here, we can see that there's an imported FE override FE window. So if we tick this box here, we can choose the FE that we want to use in our calculation. So if I go back to system deflection mode, and we can have a look at the misalignment of the gear sets and the gear meshes, depending on whether we have the FE or not. So we have a housing here in this load case, and we have one with no housing here, and you can see that there's 11 microns of total equivalent misalignment difference, and also we have 8 microns in the other gear mesh as well. So that's something that is also worth considering in MASTA, is whether you need to put your housing in. Okay, so when we specify these settings on the load cases, we can do this in the load cases and duty cycles window, but you'll notice that all of these are only done for an individual load case. So you may want to specify or override the misalignment on this gear set for all of your load cases. Now, if you've got thousands of load cases, that could be very tedious. If we go into any analysis mode, and we'll go into system deflection mode, as that's what the webinar is about, we will go. We can go onto the gear mesh, and we can see that if we go into duty cycles at the bottom and select all, we can override the properties in this properties grid here. Now, all of these can be overridden for this one component. So there's a good chance that you've got less components in your system than you have, or less gear meshes in your system than you have load cases. So it's probably easier to specify it this way for certain things. We can do this with the bearing as well. You can have a look at the internal clearances and the temperatures as well. We can specify that here for all of the load cases as well, just for the one component. Okay, I've got a couple of questions here. The first one, so the loads with the efficiency will change. So if I go back to a 2D view here, so we can see that the input, where we go for the power flow view. So as the power flows past here, we'll have some bearing losses here. And as this moves through the system, we can then see that we'll go through a gear mesh and we'll have some mesh losses. So through the system, it will keep adding up. So if I go into this load case here with efficiency turned on, we can see the power losses in the mountable components. So we see here that for the input shaft bearing here, we're going to lose 0.1234 watts. And and then this power, when it goes through the system, will be lost, and then because of that, the forces will be changing in the system. The thermal expansion, efficiency, and fitting effects. Yes, so I think I missed that when I said that you can specify all of them on the properties grid at the same time. So if we go to all here, the efficiency, thermal expansion, and fitting effects will all be turned on from here. So in the load case settings, we can go to transmission efficiency. So this is where the efficiency will be changed or turned on. And we have include thermal effects and include fitting effects here. So that will affect the whole model. For the left and right axial clearance bearings, yes, something that I missed there. If I go back to this other model here, so the axial clearance bearings will only work in a single direction. So if we go back to exactly where we were before, so this axial clearance bearing here will have a clearance, and that will only happen going, as you can see on your screen, from left to right. If the bearing moves in the opposite direction, it will have no stiffness at all. So if they both have 50 microns of clearance, then the total will be the sum of the two. Okay. If anybody has any more questions, then I'd be more than happy to either answer them now, or I'd be able to get a more in-depth explanation back if that's what's required. As always, if you have any questions about MASTA at all, if you can send us an email to support@smartmt.com. And we will do our best to get you a response or a solution to your problem as soon as we can. We also will be having some more webinars in 2020. We're just finalising that. And yeah, I'll leave it open just in case you want to ask any more questions. But thanks for joining today's webinar, and we hope to see you at the next one.